In this video, we will talk about diagonalization and the eigenvalue problems for tensors. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. First, we'll talk about diagonalization, which is finding a particular coordinate system in which the matrix that represents your tensor has non-zero entries only along its diagonal. So you're making a diagonal matrix with entries only on the diagonal. And there's examples of applications, several of them. But then we'll go ahead and develop the diagonalization equations that we're going to use. So first of all, we're going to say that the off-diagonal elements of the tensor are 0. The way we express this is here we have our tensor and we have it written in a standard basis, sigma ij e to the I, e to the j. And this, can be represented as a matrix. As we talked about a tensor of rank 2, often we use a matrix. I would denote the row and j denotes the column of the element. To say we want all the off-diagonal elements of the tensor 0, well, we want another coordinate system, and usually we denote that with the prime, so our primed coordinate system, and usually we have rs. But what we're saying here is that if r does not equal to s, in other words, if we're not on the diagonal, that element will be 0. So all we're left with are the diagonal elements, so our primed ss, e to the s prime, e to the s prime. We're going to derive this in more detail, but I'm still going to give you an outline just so that you've seen it more than once. So here we're going to dot our tensors. So this left-hand side of the equation with E1. And then we'll dot this far right-hand side of the equation also with E1. So you can see since ES and E1 are both in the primed system, that's going to give us a delta of S1. And then when we simplify this here, that means this can become sigma of 1, 1 prime and E1 prime. So this is our eigenvalue problem here. We want a tensor dotted with a vector will be equal to a scalar multiple of that same vector. And remember, because this is simply an element in the matrix, an element of the tensor. So this is a scalar. So it's our tensor dotted with a vector is equal to a scalar multiple of the vector. You might recognize this if you did linear algebra and you looked at eigenvalues and eigenvectors. The eigenvectors were those that were transformed to a scalar multiple of the original vector. So that's exactly the same idea here. So just to kind of make our notation more similar to when we did linear algebra, we're going to denote this sigma 1, 1 prime as our lambda 1. So it looks like an eigenvalue. We continue to manipulate this because now we need to figure out how we can solve for these eigenvalues and then find the eigenvectors, the associated eigenvectors. And the idea is we subtract lambda 1 E1 prime from both sides of this equation, and then we use the Kronecker delta to multiply by our lambda 1 to get this form here, which is equivalent to this matrix equation, and I'll show you how they're equivalent. I'll go through the indices and show you they are indeed equivalent. So we have this matrix equation. This is the same matrix equation in index form, which actually you should get used to the matrix equation in index form as well. But from linear algebra, we have a theorem that says that this has solution, or this matrix equation has solution, when the determinant of the coefficients, this part here, is equal to 0. So that's how we find our lambdas. Once we find our lambdas, we plug them back into this equation here, this matrix equation, to find our vector here, our A, our eigenvectors. This is the example we will do, and we'll do one other example because your book gave us 2 examples for this chapter. And the last thing I'll mention is Hermitian matrices, that matrices of interest in physics and engineering are typically Hermitian, and a matrix is Hermitian if it's equal to its complex conjugate transposed. And there are 2 important properties of Hermitian matrices. First, their eigenvalues are always pure real numbers, and second, their eigenvectors are always orthogonal. And that is significant because not all matrices are diagonalizable. There's this theorem that says, from linear algebra, an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors, but orthogonal eigenvectors are linearly independent, so Hermitian matrices can be diagonalized. So first, just to talk about what diagonalization is, we want to find a particular coordinate system in which the matrix array representation of the tensor has non-zero elements only along its diagonal. This here is an example of a diagonal matrix, and this here is the transform. These two matrices transform this matrix into the original tensor that we have. So here this tensor has been transformed into a diagonal matrix. And remember, just to remind you what tensor transformation looks like, so a vector expressed in a primed and unprimed system is still the same vector. Likewise, the expression for a second rank tensor in the two systems must obey the following. A second rank often is represented by a matrix. So our T prime is equal to, that's our primed, our primed coordinate system is equal to A, where A is a transformation matrix, our T in an unprimed system, and A transpose, where A, our transformation matrix, is gotten by dotting the basis elements, the basis vectors of our primed system with the basis elements of our unprimed system. For diagonalization, our matrix, we're going to get that with our eigenvectors. But here's kind of an example of what a diagonal matrix looks like right here. And again, we say it's diagonal because the only non-zero entries are along the diagonal. And then one other note, just to talk about an example of an application. So a rigid body will experience no vibration when rotated around any of the three axes of a coordinate system in which the moment of inertia tensor is diagonalized. And the process of balancing a wheel of an automobile makes use of this fact. So now we'll go ahead and look at some of these derivation of how we get to the characteristic polynomial. And we'll start over here. So we start with diagonalization and the eigenvalue problem kind of to derive the equations. So here we have our tensor and we represent it in a standard basis, sigma of ij, e to the j hat, and e to the I hat, e to the j hat. So these elements here, the tensor elements, sigma ij, and the basis vectors, the e to the I and e to the j of the unprimed system are presumed to be known. And what we want to do is we want to transform this to another coordinate system, which we'll call st. So that's sigma prime of st, e to the s prime, and e to the t prime. So this is our primed coordinate system. And we want to transform it to a particular primed system, and that's where all the off-diagonal elements of the tensor are zero. So in other words, if we have e to the st and s is not equal to t, so it's not on the diagonal, we want those to be zero. So all that's going to be left are our sigma of ss elements. So now, again, we want to solve for this primed system because we want to find the tensors where there are only entries on the diagonal. And we're going to start by dotting with our first basis vector from our primed system. So our sigma dot E1 prime is going to be equal to, and then on the right-hand side, we also dot with the E1 prime. And the thing is now when we look at this, because these are both in the primed system, and this is an orthogonal system, then these two vectors are going to be equal to 0, except when s is equal to 1, when they're the same basis vector. So what that gives us is here we have our sigma prime of ss e to the s. This over here will then give us our Kronecker delta of s1. And then our Kronecker delta can then be simplified. It can get rid of these s's and make them 1, and then we can get rid of the Kronecker delta. And that looks like our sigma prime of ss becomes sigma prime of 1, 1, and our es prime becomes the e1 prime basis. So this equation from this left-hand side, this right-hand side, reveals an important property of the basis vectors of the system where the tensor is diagonal. So the vectors, the basis vectors, do not change. However, they can be stretched or contracted. So the sigma here is a scalar factor that's scaling our basis vector. So our tensor dotted with our basis vectors will end up just stretching or contracting our basis vectors, but there's no rotation. And to make this look a lot like what we had when we did linear algebra, and also this property here is the same as linear algebra, the significance of the eigenvectors is they were not rotated. But to make this look more like linear algebra, we're going to call this sigma 1, 1 prime, which, to remind us it's a scalar, we're going to call it lambda 1. So our equation becomes, taking this left-hand side, our tensor dotted with E1 prime is equal to lambda 1 E1 prime. And lambda 1 is called the eigenvalue of the tensor, and an eigenvalue results when an operation on an object produces a constant, the eigenvalue, times the original object. So E1, our basis vectors are the object, and then we do an operation, that's the tensor operation, and we produce a constant lambda 1 times the original object, E1 prime. The prime basis vector is called an eigenvector. So here, this E1 prime is the eigenvector associated with this lambda 1 eigenvalue. So personally, I like to kind of remember key steps in this. I don't know why. I feel like I like the derivation, but this is one step I kind of like to remember because it's our tensor written in our standard bases and then written in a different bases or different coordinate system where you only have sigma of SS. All the other sigmas, the sigma ST, where S is not equal to T, are 0. So you're just left with this over here. And then, of course, you have to dot with E1. And what I like to remember is by the time you dot this left-hand side with E1, the right-hand side becomes my lambda 1, my eigenvalue, and then my E1 here is my eigenvector. So I kind of like to remember these two steps in particular. It's kind of nice if you can kind of remember how to get there. And I've kind of kept this summary over here for your reference. I think it's important, again, the equations I tend to remember is from here to this ESS portion. And then, of course, it's really nice to remember the eigenvalue equation over here. But now we do need to do a little more manipulation because we haven't solved for our E1 prime or our lambda 1 yet. And to kind of solve this equation, this eigenvalue eigenvector equation, we're going to introduce the unit tensor, which is equal to the scalar 1 tensor, is equal to delta of the Kronecker delta ij e to the I e to the j, which, if you recall, is also the identity matrix. Now we can use this unit tensor to rewrite our eigenvalue eigenvector equation a little bit. First, I'm going to start by subtracting my lambda 1 E1 prime from both sides of the equation. So on the left-hand side, I get my sigma dotted with E1 prime minus lambda 1 E1 prime equals 0. I want to factor out my E1 prime and dot it. Here I'm going to dot it with my original sigma tensor. To dot it with, you can't really dot it with a scalar, but this is where I'm going to use my unit tensor here. So I can multiply my scalar times my unit tensor and then dot it with E1, just to get back my scalar times E1. Now I want to express this portion here in the unprimed system. So my tensor now, I'm going to write my representation for my unprimed coordinate system. So that's going to be sigma ij e to the I e to the j minus my lambda 1, my unit tensor is delta ij, and then e to the I e to the j, and I'm still going to keep this in my prime system, dot e1 prime equals 0. I'm going to pull out my e to the I e to the j from these two terms over here, and I still dot it with e1 prime. And finally, I get this equation, e1 e sub I hat times sigma of ij minus lambda 1 d sub ij times a1j equals 0. So this is the other equation I'm going to use now to solve for lambda, and then later for my primed bases. The next thing I want to do is convert this index notation equation into a matrix equation. So these two are actually equivalent, and I will show you that they are, by running the summation for I and j. And I'll start with the summations when I is equal to 1, and I'll let j go from 1, 2, and 3. So this equation here, when I is equal to 1, I'm going to have E1 hat times sigma of 1, and j is equal to 1 in this, on this line, and then minus lambda 1 and delta 1, 1, a sub 1, 1. Now I'll let j equals 2. I still have I equal to 1. I'm going to have E1 hat, my sigma 1, 2, minus lambda 1, delta 1, 2, a sub 1, 2. And when j is equal to 3, I'm going to get E1 hat, sigma 1, 3, minus lambda 1, delta 1, 3, a 1, 3. Next, I'll let I equal 2, and I'll let j equal to 1, 2, and 3. For j equals 1 and I equals 2, I get E2 hat. I get my sigma 2, 1, minus lambda 1, delta 2, 1, a 1, 1. J is equal to 1. J equals to 2, I equals to 2. E2 hat, sigma of 2, 2, minus lambda 1, minus delta 2, 2, a sub 1, 2. And then j equals 3, E2 hat, sigma 2, 3, minus lambda 1, delta 2, 3, a 1, 3. And I have the same for I equal 3, j goes from 1, 2, and 3 over here. So this here is equal to this row times this column. So it's this row, the rows are here, and the columns are A1, 1, A1, 2, and A1, 3. So let's look at this row here. So this is E1 in the E1 direction, so this is my X row. I have sigma 1, 1, and then minus sigma lambda 1, and delta 1, 1 is equal to 1, so that's minus lambda 1. Here I have, again, still in the first direction, sigma 1, 2, and then here my delta is 1, 2, so this is 0, so this goes to 0. So I still have sigma 1, 2 times a 1, 2. And then over here I have in the E1 direction, sigma 1, 3, again my delta goes to 0, so this is just sigma 1, 3 times a 1, 3. Now you can see on this next row, it's kind of the same thing. Here's my row, that's these elements, and then here it's this row times this column. So here's the column. So the row, this first element, this is E2, so we're in the E2 column. Sigma 2, 1 minus lambda 1, but the delta is equal to 2, 1, so this goes to 0, so you're left with sigma 2, 1. Here we have sigma 2, 2, but now the delta is equal to 1, so we have minus lambda 1. And then finally over here, delta 2, 3 is 0, so we're just left with sigma 2, 3. So that's this part is equal to this row times this column. And finally, you can do the last row times column is represented by these 3 lines here. Oh, and I should also say that this is an equation. So on the other side, we have the 0 vector over here. And what you may remember from linear algebra, if you don't, I'm going to remind you right now, that this matrix times a vector equals this other 0 vector. That's a set of, this represents a set of equations, right? So this represents this row times this column is equal to 0. It's like, you know, you add them. So it's like sigma 1, 1 minus lambda 1 times a 1, 1 plus sigma 1, 2 times a 1, 2 plus sigma 1, 3 times a 1, 3 equals 0. That's the first equation. Then you have this times this, so you have sigma 2, 1 times a 1, 1, sigma 2, 2 minus lambda 1 times a 1, 2, sigma 2, 3 times a 1, 3 equals 0, and then you have your last equation, sigma 3, 1, a 1, 1 plus sigma 3, 2 times a 1, 2 plus sigma 3, 3 minus lambda 1 times a 1, 3 equals 0. So remember your sigmas, these are scalars. Your lambda is a scalar, although we're trying to solve for it. Your variables are your a11, a12, a13. So you're trying to solve for your a11, a12, and a13 such that these 3 sets of homogeneous equations, homogeneous because they're set equal to 0, has a solution. And what you might remember, or if you don't, I'll remind you, for a set of linear homogeneous equations, which is what these are, if you can represent an equation with a matrix that's linear. So for a set of linear homogeneous equations to have a solution, the determinant of the coefficients must be 0. So these are the coefficients, our coefficient matrix. So I have the determinant of our coefficients. So I have our coefficients here. I have the determinant symbol with these lines equals 0. So the result is a third order equation because we have three things on the diagonal, which will determine 3 eigenvalues. And then we're going to insert the eigenvalue into the eigenvalue eigenvector equation over here to solve for A1, A11, A12, and A13. So we're going to solve for our eigenvectors, this eigenvector here, once we have the eigenvalues. And these are the 3 elements of the transformation matrix between the primed and unprimed systems that we seek, and we dot with E2 to get the second prime basis vector and E3 to get the third. So we'll do an example to see this, but these are the ideas. And I have added here, then this is our eigenvector eigenvalue equation. This is the one where we subtract lambda 1 from both sides of the equation, and then we use the unit tensor to write this as a matrix equation, which I have here. So this is our matrix equation, which represents a set of 3 homogeneous linear equations, and we're solving for A11, A12, A13. So we're solving for this vector because remember, the sigma 1, 1, this matrix here, it's a matrix of scalars. So we're solving for this vector. First we solve for the lambdas, and then we solve for the vector. We solve for the lambdas by setting the coefficient matrix, taking the determinant and setting it equal to 0. Okay, so that's kind of our summary of what we're going to do, and we're going to do an example. We're going to consider the conductivity tensor expressed in the Cartesian coordinates, and we're going to use this one here. So our representation of this tensor is going to be the matrix with vectors, column vectors 10, 0, 0, 0, 10, 1, 0, 1, 10. And we want to express this conductivity tensor now as a diagonal system. And the first thing we're going to do is look at this determinant here, set it equal to 0, so we can find the lambdas where our system of equations over here, this matrix equation, this has solution. So I'm going to subtract lambda 1 on the diagonal now. So I have 10 minus lambda, then I keep my 0 and 0. I have my 0 here on the diagonal, 10 minus lambda, I keep the 1. The 0, 1, and then again 10 minus lambda. So across the diagonal, subtract lambda. Now I take the determinant, so to take the determinant of a 3 by 3, so first I'm going to keep this element as my coefficient. I'm going to cross out this element's row and column, and I'm going to take the determinant of what's left. So I have 10 minus lambda, 1, 1, and 10 minus lambda. Next, I'm going to take the second element of my row, and I'm going to multiply that by, and I'm going to cross out the row and column, the determinant that's left, which is 0, 0 on the columns, and then 1, 10 minus lambda. Of course, I really didn't need to do that because I have a 0 in front. And actually, this should be a minus because, determinants, you keep switching the signs. Then next, I'm going to take the last row of my the last column of my first row, cross out the row and column. So I'm going to add 0, the 0 times the determinant of what's left, which is the 0, 0, 10 minus lambda, and 1. And then what I get, these just go to 0. So I have 10 minus lambda, and then I have my cross multiplying 10 minus lambda squared minus 1. So this expression here is equal to 10 minus lambda, 9 minus lambda, 11 minus lambda. When I set that equal to 0, then I get 3 solutions. Lambda 1 equals 10, lambda 2 equals 9, and lambda 3 equals 11. Okay, so what I have found is this system of equations here, this matrix equation, will have a solution for the homogeneous system if lambda is either equal to 10, 9, or 11. So we're going to solve this system of equations using 10, 9, and then 11. So we'll start with 10. Okay, so now we're starting with lambda equals 10. We're going to plug it into our matrix equation. And actually, I'm going to pretend like this is our matrix, and then because it has the particular sigma, the particular tensor we're working on, and then pretend like there's an A over here and then an equal sign and a 0 over here. So anyway, 10 minus lambda, in this case, lambda is 10, so it's 10 minus 10. We have our 0 and our 0. The next row will be 0, and then 10 minus lambda again, so 10 minus 10, and then we have our 1, our 0, our 1, and our 10 minus lambda, so 10 minus 10. And then as I said, we're going to, that's our matrix equation, our A vector, and it's equal to 0. And if you recall from linear algebra, and again, if you don't, I'll remind you, the way we solve these equations is we use the augmented, we row reduce the augmented matrix. So 10 minus 10 is 0, then I have a 0, 0, I have a 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, so 0, 1, 0, and then the augmented matrix has the solution set. This vector here on the right gets moved over here. And we row reduce it, but actually this is already row reduced enough for us to solve. And again, remember we're looking for our, we're solving for this vector now because we've already solved for our eigenvalue. We're looking for the eigenvector associated with this eigenvalue. And I also like to write, in this case, remember our A11, that's kind of represented by a first column, A12 is represented by a second column, A13 is represented by a third column, right? Because when you multiply row times column, A1 always gets multiplied by this first column, A2 gets multiplied by the second column, and A13 gets multiplied by the third column. And what that will give me then, if I read off this first top line as an equation, I have 0 times A11 plus 0 times A12 plus 0 times A13 is equal to 0. So that tells us nothing about A11 and A12 and A13 because any numbers in here, complex or even real or vice versa, it's always going to equal 0. But let's look at our next line, our next equation. So we have 0 times A11, 0 times A12, and then 1 times A13 equals 0. So that implies that A13 is 0. And our last equation, 0 times A11, 1 times A12, and 0 times A13 equals 0. So that implies A12 is equal to 0. In this case, there's no restriction on A11. So this, our solution vector, here, our eigenvector is of the form A11, 0, 0. And since we want a unit vector, and also because the numbers are easy, we're going to choose A11 to equal to 1. So our first eigenvector is 1, 0, 0. That's the eigenvector associated with the eigenvalue of 10. Also, what this tells us is, remember, we're solving this equation here. So what that is telling us is that our E1 prime, our first basis vector in the prime system, is equal to 1 times E1, 0 times E2, and 0 times E3. So here we've written our prime, our E1 prime basis vector in terms of our unprimed basis vectors. Next, we're going to look at lambda equals 9. And remember, we got here because lambda equals 9 is one of the values that makes the determinant equal to 0, right over here, which means that this system of equations will have solutions. So we're going to plug in lambda equals 9 into our system of equations. We're going to use this for our matrix though. So 10 minus our lambda, which is minus 9, and then going down the row we have 0, 0. Then we have 0, 10 minus lambda, again 10 minus 9, 1. Then we have 0, 1, and then 10 minus lambda, and then we have our matrix, our vector A, and it's equal to 0. Also, not all tensors are going to have the same number across the diagonal, so sometimes this is a little more interesting. Anyway, to solve this system of equations, we're going to row reduce the augmented matrix. Here is our augmented matrix, and I did the subtraction, so 10 minus 9 is 1. And then I have my solution vector over here. And I want to get this in row echelon form, which is kind of, remember, that staircase form. So I need to get this here to equal to 0. So I want all zeros underneath the staircase. So to get zeros, I can subtract from R3, R2. And I kind of say what it is I'm doing underneath the arrow. The first row that's listed here is the row that's being replaced. And it's being, so R3 is being, the third row is being replaced, and it's being replaced by R3 minus R2. So R1 stays because it's good in the staircase. R2 stays, it's good in the staircase, but this needs a 0 here, so I subtract R2 from it. So, but the whole row. But fortunately, because of the staircase, this stays 0. Then 1 minus 1 is 0. 1 minus 1 is 0 here. And then I still have 0 minus 0 is 0. Remember, this first column represents A11. The second column represents A12. And the third column represents A13 because when you multiply, the row times column, A11 is always multiplying this column. A12 is always multiplying the second column, and A13 is always multiplying the third column. So what this tells us here, if I read off the first equation, I have A11 plus 0 times A12, so I didn't write that in the equation, plus 0 times A13 is equal to 0. This equation here tells us 0 plus A11 plus A12 plus 1 times A13 is equal to 0, which means this implies that A12 is equal to negative A13, and this is all 0, so it doesn't tell us anything. But we have enough to make a vector. We know our first A11 is 0. A12 can be any arbitrary number, but A13 has to be negative A12. So I wrote 0, A12, and negative A12. And just for each of these numbers, I plug in 1. So I have 0, 1, negative 1. But I want to normalize. I want this to be a unit vector, so I divide by the length of this vector, which is square root of 2. So I have 0, 1 over square root of 2, minus 1 over square root of 2. This here tells us the eigenvector associated with lambda equals 9. In terms of the old bases, our unprimed bases, that's equal to 0 times E1, 1 over square root of 2 times E2, minus 1 over square root of 2 times E3. But this is my second eigenvector. Last, we have the eigenvector equals 11. So I plug it into my equation here. So I have 10 minus 11, 0, 0. 0, 10 minus 11, 1, 0, 1, 10 minus 11 times my vector A equals my 0 vector. My augmented matrix then is equal to minus 1, 0, 0, 0, minus 1, 1, 0, 1, minus 1, and then my 0 solution vector over here. In the augmented matrix, this is almost staircase, right? If I do a little staircase, if it were 4 by 4, go like that. But anyway, so this is almost staircase, but I need to get rid of this. I need a 0 underneath my staircase, so I can just add. So I'm going to replace row 3 with row 3 plus row 2. If I were replacing row 2, I'd put row 2 in front. But anyway, I'm replacing row 3. So my first row stays, my second row stays, my third row is replaced. So 0 plus 0 is 0. 1 plus negative 1 is 0. Negative 1 plus 1 is 0, and then 0 plus 0 is 0. This first column represents A11, second column represents A12, third column represents A13. So my first equation is minus A11 plus 0 equals 0. My second equation is minus A12 plus A13 equals 0, which implies that A12 is equal to A13, and then I have all zeros on the bottom. So that doesn't give me any more information, but I do have that A11 is equal to 0, A12 is equal to the same thing as A13, so I chose 1 and 1, but then of course I have to normalize, so I have 0, 1 over square root of 2, 1 over square root of 2, which tells me my third prime basis vector is equal to 0 times E1, 1 over square root of 2 times E2, and 1 over square root of 2 times E3. So now I have my 3 eigenvalues, lambda equals 10, lambda equals 9, lambda equals 1, and my 3 eigenvectors associated with them. Those are the vectors we just calculated. So for lambda equals 10, the eigenvector was 1, 0, 0. For lambda equals 9, the eigenvector was 0, 1 over square root of 2 minus 1 over square root of 2. Or for lambda equals 11, the eigenvector was 0, 1 over square root of 2, 1 over square root of 2. The thing is, in your book, it says there's an ordering ambiguity, because I factored and I simplified this way. But, someone else could order it differently. So as a convention, what we do is we set up the primed system to be right-handed. So the ordering and sign choices will give you prime basis factors shown below. And actually, I'm going to show it above. But the idea is, first I graphed in yellow, which is why I underlined it in yellow, the vector 1, 0, 0. And I chose my first bases to go up, my second to go to the side, and third to go out to the other side. This is sort of patterned after your book. They like 1 to go up. 2 to go out, and 3 to go to the right. So when I graphed 1, 0, 0, that's 1 in the first bases. So that's just straight up. My second one, basically it's kind of not at all up, but it's in this 2, 3 plane, and it's 1, negative 1. So 1 in this direction, negative 1 in the 3 direction. So I get something like this. This is in green. Whereas in blue, I get something right at the 45 because it's 0, 1, 1. So the thing about this is if you think of curling your right hand, you curve your fingers from green to blue, then the yellow will point straight up. And also these two are in the same plane, the green and the blue. So think of curving them in the same plane, and you'll get this third one here. So what this suggests is that your first vector should be the green, the second should be the blue because you're curling from the green to the blue, and you finally get the yellow. So this should be our first vector. I'm going to number it. The blue should be our second because you curl from the first to the second, and then you get the third one is perpendicular. That means our conductivity tensor here, our 10, 0, 0, 0, 10, 1, I'm reading the columns, 0, 1, 10, should equal to our diagonal our diagonalized matrix, or our diagonal matrix, is going to have 9 as our first eigenvalue, 11 as our second, and 10 as our third. So we started with 9, 11, 10, which means for our transformation matrix, in the same order, we're going to do the eigenvectors. So it's the 0, 1 over square root of 2 minus 1 over square root of 2. Then we did the 11. So the vector associated with 11 is 0, 1 over square root of 2, 1 over square root of 2. And then we did 10. So the vector associated with 10 is 1, 0, 0. And what we have then is this matrix is going to equal to our transformation matrix times our diagonal matrix times the transpose of our transformation matrix. And this is coordinate change, right? It's what we had worked on in the previous video when we were doing transformations on rank 2 tensors, right? We said the rank 2 tensors were like matrices, and in matrix form, our transformation was T prime is equal to our transformation matrix A, our unprimed system, and then our transformation matrix transposed. And as I said, we had this formula here in our previous video to get the matrix, but in this case, we use the eigenvectors. But in effect, if you remember, when we wrote our eigenvectors for the primed system, these vectors were the coefficients of the eigenvector of the primed system using the unprimed system as a basis. So we were kind of using this formula here, or this fact here, that when we talked about doing transformation matrices, if we knew the basis of both coordinate system, then we could write the transforms as one basis as expressed as a linear combination of the other bases, which is exactly what these eigenvectors are. And also, just to verify that this diagonalization worked, so here's my original tensor, here's my diagonalization. So I multiplied my A matrix times my diagonal matrix, and this was the result of the product of these two matrices. And then I multiplied by the transform of the transformation matrices, and I got this here. And then when I did all the additions and stuff, I got back my original matrix. So that was just to verify that I did do my transformation correctly, or my diagonalization correctly. So that was sort of long, but I have one more example, and this one will go quicker since we kind of know what we're doing. And also this one is an example where there's only 2 eigenvalues, but that's okay because we'll get 2 eigenvectors. I'll show you how that works. And by the way, this is a Hermitian matrix. Now we're looking when this system of equations has solutions, the homogeneous system has solutions, which means we need to look at the determinant, set it equal to 0, and find the eigenvalues that will give us 0. So here I have our matrix, and along the diagonal, I subtract lambda. So I have 11 minus lambda, 11 minus lambda, and 10 minus lambda. The rest of the matrix stays the same. So my determinant, reading off the columns, is 11 minus lambda minus 1, 0, minus 1, 11 minus lambda, 0, 0, 0, 10 minus lambda. Then again, to take the determinant, I take my first, I go across the top row, expand across the top row, and I start with my first element, so that's 11 minus lambda. I cross out the rest of the top row and top column, and I take the determinant of what's left, which is 11 minus lambda, 0, 0, 10 minus lambda. Next, expanding, I do a minus times this second element, so that's a plus 1. I cross out the column and I cross out the row, and I take the determinant of what's left, which is minus 1, 0, 0, 10 minus lambda. And then I expand along the last, but that's just a 0, so I just have a 0. So I have 11 minus lambda taking this, then that the determinant of what's inside, I cross multiply and I get 11 minus lambda times 10 minus lambda minus 0. So I have 11 minus lambda squared, 10 minus lambda. And here I have 1 times minus 1 times 10 minus lambda minus 0. So this is equivalent to 10 minus lambda squared, 12 minus lambda. So my eigenvalues are 10, 12, and 12. So these two are repeated, but that's not a problem, or it won't be a problem, and you'll see why. We will start with lambda equals 10. So plugging into our matrix equation, we have 11 minus 10, and then going across the row, we have minus 1, 0. And then we have minus 1, 11 minus 10, 0. Then 0, 0, 10 minus 10 times A equals the 0 vector. Our augmented matrix then is 1 minus 1, 0, 0, minus 1, 1, 0, 0, 0, 0, 0, 0. To make this row in echelon form, right, everything under the staircase needs to be equal to 0. So we need to work on R2, but we can just add it to R1, and then we'll get our first row stays, but we'll have R2 plus R1. So negative 1 plus 1 is 0, 1 plus negative 1 is 0, then we have 0, 0, and our last row is 0. So there's not a lot of information here, except that A11 minus A12 plus 0 equals 0, which means that A11 is equal to A12, and there's no restriction on A3. So our vectors look like this. A11 and A12 is equal to A11, and then we have A13. But A13 doesn't depend on A11. So A11 looks like A11 times 1, 1, 0. This is like when A11 is equal to 1, just because I chose easy numbers. The thing is we can't put A13 here because it's not dependent on A11. It needs to be its own vector because it can do whatever it wants. It's not dependent on A11 or A12. So A13 is equal to 0, 0, 1. So normalizing this vector, we have 1 over square root of 2, 1 over square root of 2, 0, and then 0, 0, 1. These are our two eigenvectors associated with lambda equals 10. And again, just to look at how we got the two eigenvectors, so in general, our solutions are of the form some number in the first coordinate, another number in the second, the same number for the second coordinate, and then this third number in the third coordinate that has nothing to do with the first two. It doesn't have to, it can be equal, but it doesn't have to be. It could be equal to negative, but it could be whatever it wants. So this vector here, A11, A11, A13, is equivalent to this, A11 times 1, 1, 0 plus A13 times 0, 0, 1, right? So if I multiply and I add, I get this vector here. So that means this is my first basis vector, but I normalize it. This is my second basis vector. It's already normalized. Now for lambda equals 12, plugging into my matrix equation, I get 11 minus 12. Going down the row, I have minus 1, 0. Then I have minus 1, 11 minus 12, 0, 0, 0, 10 minus 12 times my A vector equals my 0. My augmented matrix then is here 11 minus 12 is minus 1, 1, 0, 0. The next row is minus 1, 11 minus 12 is minus 1, 0, 0. And then 0, 0, 10 minus 12 is minus 2, and 0. So to row reduce to get into echelon form, right? The only thing that needs a 0 is over here. So I'm going to do R2 minus R1. That's an R2 minus R1. Sorry, kind of got mushed together. So R1 stays the same. -1 minus 1 is 0. -1 minus 1, -1 is 0. And I have 0, 0. And then my third row stays the same, 0, 0, -2, 0. My first column represents A11, second column represents A12, third column represents A13. So reading off this first equation, I get minus A11 minus A12 plus 0 A13 equals 0, which implies A11 is equal to negative A12. And then my last equation tells me my minus 2 A13 equals 0, which implies A13 equals 0. So my vectors, my solution vectors, are of the form A11 minus A11, 0. In other words, 1 minus 1, 0 will do it, except we want to normalize. So we have 1 over square root of 2 minus 1 over square root of 2, 0. So this is the eigenvector for lambda equals 12. Looking at my eigenvectors again, I have, I'm not going to worry about normalizing, but I have one in the 1 direction and one in the 2 direction. So in the 1, 2 plane, and also 0 in the 3. So in the 1, 2 plane, I have this yellow vector. Over here, in the along the 3 axis, I have 1 unit over here. So it's totally not in this plane. Then over here, I have, again in the 1, 2 plane, I have something in the positive 1 direction, but in the negative 2 direction. So it kind of goes out this direction. But these two are in the same plane. So if I curl from blue to yellow with my right hand, I'm sorry, I dropped my stylus to curl my fingers. From blue to yellow, you'll see you get this third vector here. And remember, these are in the same plane, you're going to get something perpendicular. So I'm going to curl from blue, that's 1, to yellow, that's 2. And then the perpendicular one is this green vector 3. So what I have is my original tensor. So reading the columns, 11, -1, 0. -1, 11, 0, 0, 0, 10 is equal to my transformation matrix. So I need my first eigenvector, that's the blue. So that's going to be 1 over square root of 2 minus 1 over square root of 2, 0. Then I'm going to go to my yellow eigenvector, 1 over square root of 2, 1 over square root of 2, 0. And then finally my green eigenvector, 0, 0, 1. This transformation matrix times my diagonalized matrix. So first I need my blue eigenvalue, which is 12, 0, 0. My yellow eigenvector in the second position, so it's 0, 10, 0. And then my last eigenvector is 12 in the, is that right? No, sorry, 3 is, where's my eigenvector? I didn't, oh, it's also, is this the one that's also 12? No, this is the one that's also 10. So another 10 in the third position, 0, 0, 10. And then over here, I need my transformation matrix transpose. So this first column becomes the first row, the second column becomes the second row, and the last column becomes the last row. And you can multiply this out. So I multiplied A times my diagonal matrix, and this was my resulting matrix, and then I multiplied times my A transpose, and you can see when I worked out all the numbers, I got my original tensor. So my diagonalization was correct. And thank goodness, too. So to review what we have done in this video, we looked at diagonalization, which is to find a particular coordinate system. So we would transform to a new coordinate system in which the matrix array representation of a tensor has non-zero elements only along its diagonal. And there was examples in physics and actually examples also in your linear algebra textbook. So what we looked at is the diagonalization and eigenvalue problem. And the idea is if you want the off diagonals of the tensor to be 0, that means your tensor, you can write it in your standard bases, or we can look for the transformation where the only sigma elements are those where the I equals j, or in other words, the sigma prime SS. Okay, everything else where I does not equal to j will be equal to 0. What we did to figure out how to solve this equation here is we dotted both this extreme left-hand side with this extreme right-hand side with E1. We found that these two here, then the ES prime and the E1 prime, since they're both in the prime system and they're basis vectors, that means they're equal to 1 when S is equal to 1, and they're equal to 0 when S is not equal to 1. So that gives us the Kronecker delta of D of S1, which means we can simplify by changing these S's to 1 and getting rid of the Kronecker delta. So that gives us our left-hand side here times now our S's become 1. So sigma 1, 1, E1. Remember your sigma 1, 1, that's just an element of a matrix when you're looking at a second-rank tensor. And actually, it's just an element of any tensor. So this is a scalar. So we're going to call it lambda 1 because then it looks more like linear algebra. So what we have is our tensor dotted with a vector is equal to a scalar multiple of that original vector. So this here is our eigenvalue equation, just like from linear algebra. The next thing we did is subtracted lambda 1 E1 prime from both sides of this equation, and then we used this Kronecker delta so we could get this matrix equation. This is the index form of the matrix equation, and then we showed that's equal to this form of the matrix equation. From linear algebra, we said that this homogeneous system of equations has solution if the determinant of the the coefficients is equal to 0. The coefficient matrix is equal to 0. So we set the determinant equal to 0 to find which lambdas of this matrix will give us solutions. Once we have our lambdas, we plug in our lambdas one at a time into our matrix equation to solve for our vectors, our eigenvectors A11, A12, and A13. We did 2 examples over here. And then the last point was that Hermitian matrices, they're of particular interest in physics and engineering. They're typically Hermitian. And a matrix is Hermitian if it's equal to its complex conjugate transpose. And there are 2 important properties of Hermitian matrices. First, their eigenvalues are always pure real numbers. And second, their eigenvectors are always orthogonal. And that's important because not all matrices are diagonalizable. But we have this theorem from linear algebra that says an n by n matrix, also matrices have to be squared to be diagonalizable. So an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors, and orthogonal eigenvectors are always linearly independent. So if you have a Hermitian matrix, you can always diagonalize it. And that's it for this video. Thank you for watching.